talk through this Tums and Rolaids pre-lab, just part 1 and part 2 of the pre-lab. We'll do part 3 tomorrow. So the question really is Tums or Rolaids better? Is Tums or Rolaids better? I don't know. This isn't grammar class. Most effective at neutralizing stomach acid. So Tums and Rolaids, if you didn't know, they are actually bases. Right? And so that's why they help to neutralize acid, because they react with the acid, taking some of the H plus out of your stomach. So if you have extra stomach acid and you start to have heartburn, then you can take Tums or Rolaids for that. So we're going to see which one is better at doing that. All right, so we're going to go through some pre-lab problems, and this will kind of help you see what you might want to do with your post-lab. All right, and this will also be a good review over sections 4, 5, and 4, 6, because we're doing a lot of molarity type calculations here. So, first pre-lab question here, starting with an NaOH solution that is 1.5 molar. How many milliliters of the stock solution are needed to make 250 milliliters of 0.15 molar NaOH? Okay, so we've got, well actually, this one, okay, it stayed on there. There's a couple of different formulas you probably will need to know in order to be able to do the calculations you have to do here. One of them, and we talked about both of these last year, one of them is molarity equals moles over liters. Okay, now the moles is the solute, the thing being dissolved, and the liters is the solution. Okay, so if you want to find the concentration of something, you take the moles of whatever you're dissolving divided by the total liters of solution. That will give you the molarity. Now another equation that is useful here, if you're diluting a solution, then you need to use the equation M1V1 equals M2V2. Okay? We talked about that last year, didn't we? M1V1? Okay. So this problem right here, you're given an initial concentration, okay? It's asking how many milliliters, so here's a concentration. How many milliliters, so that's a volume. And it's asking how many of those are needed to prepare 250 milliliters, so there's another volume. And it's giving you another concentration, 0.15 molar, so that's an M2. Okay? So this looks to me like an M1V1 equals M2V2 problem. Okay? So that's how you're going to set this one up. And basically what you're trying to figure out is how many milliliters of the more concentrated NaOH do I need to put in, and then dilute it to 250 in order to make it a 0.15 molar solution instead. Okay? And so you'll just plug this into the equation, 1.5 molar times V1, whatever V1 ends up being, that's what we're trying to solve for here, equals 0.15 molar times V2, which is, now the nice thing about M1V1 equals M2V2 is it doesn't have to be in liters, it can just be in milliliters. So we'll just plug in 250 milliliters here. And then just solve for V1. Alright, so we'll do that. Should get V1 needs to be 25. 6 figs, okay, just 2, so 25 milliliters. All right, now what that's telling me, the important part is understanding what that's telling me. I need to add 25 milliliters of the initial solution and then dilute that, add water until I'm up to 250 milliliters, and that will give me the 0.15 molar solution that I need. Okay? So that's how that one works. Oh yeah, I forgot the answers are on here. I'll work it out this way because I think it's better if you see it being worked. Okay, number 2. At the end of a neutralization reaction, which is the equivalence point, what is the relationship between the number of moles of H plus and OH minus present? Okay. So we need to talk about this a little bit. And the classic example here is if you react HCl, well that's weird, why is it doing that all of a sudden? HCl plus NaOH, okay? And you can kind of think of this as a wife swap from last year, even though we know that those don't really exist. But the H plus ends up going with the OH minus, and it makes H2O. And then you end up with NaCl. All right? So if you're doing a perfect neutralization, then you need to have the same number of moles of H plus and OH minus present. And all of this, the net ionic equation for this reaction right here is H plus plus OH minus yields H2O. Okay? So at the equivalence point, let's say that you have 1 mole of H plus. Because remember, we're talking about a titration here, right, where we're adding base to the acid. So if you have 1 mole of H plus in your solution, you have to add 1 mole of OH minus to completely neutralize it, right? So at the equivalence point, there should be the same number of moles of H plus and OH minus. Does that make sense? Okay. Number of moles of H plus will be equal to the number of moles of OH minus. All right. So number 3 here, we know chemical reactions occur by some sort of evidence. So we're looking for color change, maybe a precipitate, heat, formation of a gas, those sorts of things. In this reaction, we just want to talk about what is the color of each reactant and product. Now, I don't expect you to know this off the top of your head necessarily, especially for the KHP, which is potassium hydrogen phthalate. I'll just tell you that one is in solution, I think is what they're asking about here, because that's really the important part. Because we're going to have this in solution, well, it says it's in solution because it's aqueous, right? So this is going to be colorless or clear, however you want to say that. Sodium hydroxide is also clear or colorless. Potassium sodium phthalate, also colorless. And we know that H2O is colorless. So that's kind of a problem, because how can we even tell if a reaction is happening here? Because for this one, there's really not even much heat released, and there's definitely not a precipitate. So it's really hard to tell if a reaction is happening or not. I mean, one way we could do it is we could hook it up to a pH meter, right? And what we should see as we add the base to the acid, we should see the pH starting to go up, right? Because acidic is low pHs, like 0 to 7, okay? And as we add the base to it, we should start to see that pH go up a little bit until it gets to 7, and then we would know we're probably at the equivalence point. But without a pH meter, we're kind of in trouble unless we do something else. Okay, so that's where this question is kind of trying to lead you here. Many titrations involve reactions that, like this one, offer no visual evidence. Okay, so in those cases, that's why we would use an indicator. So that's the phenolphthalein that I used back there today. Okay, it's sensitive to its chemical environment. And phenolphthalein is the one that we're going to use for this lab because it's just a very common one that gets used for acid-base titrations. So if phenolphthalein is used, how will we know when the endpoint is reached if we're adding the base to the acid? What's going to happen? Yeah, you're going to get that light pink, right? I'll just PowerPoint answer that one. So some of you are getting annoyed with me today, right? The addition of 1 drop of base will cause the solution to stay pink, okay? Just a very faint pink. And that's a good titration when you can add 1 drop and you can get it to stay. Now, just, we're not going to do the titration this way, but let's say that I was adding the acid to the base instead, okay? So I put the indicator in the base and I was adding the acid. Then what would I be looking for? Yeah, I would look for it to go from pink to clear, and that's how I would know that I reached the equivalence point. Okay? All right, KHP, potassium hydrogen phthalate. That's a hard word to say. It's PHTHALATE. It's a monoprotic acid. That just means it only gives away one hydrogen in solution. And it has a molar mass of 204.23 grams per mole. Okay, so let's say that we use a mass of 0.824 grams of KHP, put it into an Erlenmeyer flask. Just hypothetically, let's say that we do that, you know. Not that you have to do that on your procedure or anything, but let's just hypothetically say that's what you do, okay? Because this is just a pre-lab question. So you've got 0.824 grams of the KHP. You put it into an Erlenmeyer flask, and then you add distilled water to it to dissolve the KHP. Now the nice thing about some of these pre-lab questions, I will say this, is that if you were dissolving KHP in water, you might not know exactly how much would dissolve in water, right? You might put in way too much, and then you end up with some solids sitting at the bottom, and that's probably not good, okay? So by looking at a pre-lab question like this, you can at least get some sort of sense of how much KHP you would want to add to how much water in order to know, to make sure it all dissolves, right? Okay, so you add distilled water to the flask to dissolve the KHP, and then you put in 3 drops of the phenolphthalein indicator. Again, it doesn't have to be 3 drops. This is just a pre-lab question, you know. But a portion of the NaOH solution to be standardized is added to a 50 milliliter buret, which is the kind of burets that we have back there. And then we titrate the KHP with NaOH solution to a faint pink endpoint. The titration took 26.20 milliliters of the NaOH solution. What is the concentration of the NaOH solution? Okay, that's a little tricky. So what we have to think about here is we have to think about the reaction that's taking place. Now the reaction was given to us right here, okay? So notice this reaction, there's one hydrogen here, that's why it's called monoprotic, okay? And that H plus is probably going to end up reacting with this OH minus, and it seems like it's going to react in a nice 1-to-1 ratio here. Okay, so that makes our calculation kind of easy. The problem is we have to figure out how many moles of H plus we actually have, right? And so, but that's not that hard because we have a mass of KHP. We have the molar mass of the KHP, right? So let's start there. We've got 0.824 grams of KHP. We'll go from grams to moles. 1 mole, there's 204.23 grams. It's going to be an unfortunately small number. So then you end up with about, the right number is sig figs, 0.00403 moles of KHP. And you can put that in scientific notation if you're more comfortable with that. So that's the number of moles of the KHP, right? So for every 1 mole of KHP, we have 1 mole of H plus. All right? And so that's also how many moles of H plus we have in that solution, okay? Now this titration requires 26.20 milliliters of the NaOH solution. So we want to know what's the concentration of the NaOH solution, okay? So we know how many moles of H plus we added. And then the other thing that we know here that we have to remember, at the equivalence point, the moles of H plus is going to be equal to what? Well, okay, it's equal to KHP, but what else? At the equivalence point, the moles of H plus should equal, I hope this doesn't erase this when I go back. There's one of the other pre-lab questions here. Whoops. See, I wrote all over it. At the equivalence point, H plus is equal to OH minus, right? Okay. So we can use that little piece of information here. So basically, at the equivalence point, we know that we had to have added 0.00403 moles of OH minus in order to react with all of that H plus. Okay? All right, so now this doesn't seem so bad anymore because now we can just use our molarity equals moles over liters equation, right? And if we know the number of moles of OH minus we have, and we know how many liters of OH minus we added, or basically the NaOH solution that we added, then we should be able to figure out the original concentration of the solution, right? So let's see here, 0.00403 moles divided by, and here's where you have to be a little bit careful. We have 26.20 milliliters, and on this one you do have to change it to liters in order for it to work. So you just divide that by 1,000, 0.02620 liters. Okay, and we work that out. Should give us a concentration of about, so the right number is sig figs 0.154 molar. Okay? Now what we just did is we standardized the NaOH. Okay? So now if you look back over here, it tells us, which question is it? Oh, I think it's the first question, okay? So we made what we were hoping was about a 0.15 molar solution of NaOH, right? Okay? So to standardize it, you figure out exactly what the concentration of that NaOH is. So we added it to the KHP, and we figured out that the exact concentration is 0.154 molar. So that's pretty close to what we were shooting for, okay? But you have to do this standardization part to make sure that it's exactly what you want it to be, okay? Whoops, sorry, this is all. I should probably, well, I like doing it this way. All right, so the next question here, second titration yielded a value of 0.152 molar in NaOH. All right, so we got 0.154 one time. We got 0.152 in the second trial. That's interesting. It's a pre-lab question in which you do 2 trials of an experiment. I mean, that's just kind of interesting, I think, you know, but we're just doing pre-lab here. It's not like you have to write this into your procedure or anything, okay? All right, so we're just finding an average here. That's a pretty simple calculation, right? And you probably don't even have to do the calculation to figure out if you take 1.152 plus 0.154 divided by 2, it's going to give you 0.153. Okay? So there's that. Okay, number 7. Starting with an HCl solution that is 1.0 molar. Okay, now notice we are standardizing the hydrochloric acid solution, okay? So we just got done standardizing the NaOH solution because we used an acid to do that. So now we can use our standardized NaOH and we can standardize the hydrochloric acid. Okay, so now are we on part 2 now? Okay. So part 2 should go pretty fast after what we just did because the calculations are very similar. So we're starting with a 1.0 molar solution of HCl. And we want to know if we're trying to make a solution that's about 0.1 molar HCl, we need to know, okay, how many milliliters of the original solution do we need? So this is the exact same M1V1 equals M2V2 calculation that we just did, okay? If this is our M1 right here, the 1.0 molar, then this would be our V1. That's what we're actually trying to find. We'll call this our V2, the 250 milliliters, and this is our M2. Okay, so just plug everything in and solve it. 1.0 molar times our volume, which is what we need to know here, is equal to M2, which is 0.10 molar, times 250 mils. Again, with the M1 V1 equals M2 V2 equation, you do not have to change it to liters. You can keep it in milliliters. All right, so then when we calculate that, I should be, yeah, why am I doing that on a calculator? 25 milliliters, right? And again, to the right number sig fig, it's just 25. So that's how many milliliters of the 1.0 molar we would need to start with. Take 25 milliliters of the 1.0 molar, and then dilute that down until you have a 250 milliliter solution. So you're just adding water till it gets to 250 mils, and that's going to make us a 0.10 molar HCl solution. Oh, by the way, here, let's tie this into something we talked about the other day on the AP chemistry course description. Hang on just one second. Okay, sorry about that. So let's see here. Oh, okay, I remember what I was going to say. So we got this one answered.
Dr. Gwynn, contact the main office, please. Dr. Gwynn.
Okay, lots of interruptions. So my question was going to be, what would be the best piece of lab equipment to use to prepare this solution? Just thinking about what we talked about with the AP chemistry new course description the other day, can you think of what that piece of equipment would be in order to make, now not do the titration, right, but to actually make the solution, to dilute it down so that you're adding it up to a 250 milliliter mark, perhaps? Remember what those are called? Close. It's not an Erlenmeyer flask. Yeah, my great drawings of these. The volumetric flask is what that's called. So if you find a 250 mil volumetric flask, okay, with the one line on it, that would probably be the best thing to use in order to make this solution. Okay, that would be a good place to talk about that. So 25 mils. All right, so we've got the HCl solution. We have now made what we think is about a 0.1 molar solution, but we want to make sure. Okay, so now that we have a standardized NaOH solution that we know is exactly 0.153 molar, we can use that solution, titrate it with the HCl, and we can make sure we can see exactly what our HCl solution is supposed to be. Okay, or not what it's supposed to be, but we can see exactly what it is. So from the buret, 20 milliliters of this solution is added to a clean, dry Erlenmeyer flask. About 50 milliliters of distilled water is added to the flask, again along with 3 drops of phenolphthalein. Or, you know, I'm just going to say it, I don't have a lot of phenolphthalein. Please don't use a lot of drops of phenolphthalein in your procedure, all right? You only need about 3. All right, so this solution is then titrated with the standardized NaOH solution that we got from part 1, which again was 0.153 molar, I think was the average. And again, we're looking for that faint, persistent pink endpoint. It took 13.33 milliliters to get there, so we want to know what's the concentration of the HCl solution. Okay, so once again, the key here is that at the endpoint, at the equivalence point, those basically mean the same thing. We'll talk more about the terminology, but the endpoint and the equivalence point are essentially the same thing. We want to know how many moles of something do we have here. Okay. Now on this one, we know that we have 20 mils of the HCl solution. Okay. Oh, we also know that we added 50 milliliters of distilled water to the flask. So we're diluting it even further, right? That's kind of important. And then we titrate the solution with the standardized NaOH solution to a faint but persistent pink endpoint. So to reach that endpoint, we've got to get to 13, or we have to add 13.33 milliliters of the NaOH solution. Okay. So you might struggle a little bit with where to start here. But what we know, this is how much NaOH we had to add, and we know the exact concentration of that NaOH because we just standardized it, right? So we know a concentration, we know a volume, right? So that maybe would make you think about this equation, possibly. Because then we can figure out the moles of the NaOH that we added into that solution, and that's going to help us figure out the moles of the H+. All right, so we've got, I keep forgetting our concentration. It's 0.153, right? 0.153 molar is equal to the number of moles, that's what we're trying to find, divided by the number of liters. Now, again, you have to change this to liters, so it's going to be 0.01333 liters. Okay? This one I cannot do in my head. That's going to give us 0.00204 liters, no, not liters, moles. Of the NaOH that was added, okay? Now, that's helpful in a couple of ways, because we can say, because the Na and the OH are present in a 1-to-1 ratio there, we can say that that also equals, that means that we have 0.00204 moles of OH minus, okay? That's how many moles of OH minus we added in order to get to the equivalence point, okay? So what does that mean? If that's how many moles of OH minus we have, what else does that tell us? That tells us exactly how many moles of H plus we have, right? So we have 0.00204 moles of H plus in that solution, okay? Now I've got to think a little bit, because I've got to get back to what I really want to find out is what's the concentration of that HCl solution, okay? What's the concentration of the H plus in the HCl solution? Does this matter in my calculation? I made it more dilute by adding the 50 mils, right? So I did change the concentration before I did the titration. But did I change the amount of H plus that was in there? I mean, all I added was water, right? So it should be, if I have 0.00204 moles in the diluted solution, I should also have 0.00204 moles in the original solution. Does that make sense? Okay? So actually, it doesn't really matter that I diluted it. Now, so then why did I do it? And what was the point of this person diluting this solution before adding the NaOH? Okay, yeah, this one's kind of tricky, but there's a good reason for this. And the main reason is we're going to conserve NaOH that way. Because if you dilute it, then it takes less of the NaOH to reach that equivalence point, right? You only have to add 13.33 milliliters. If we hadn't diluted it, we might have had to add 20 or 30 milliliters, okay? So this just makes it a little bit quicker to get to the endpoint, all right? So again, another good thing to keep in mind for your procedure, but do what you want, okay? All right, so we know that we've got 0.00204 moles of H plus in there, okay? We also know that we had 20 milliliters of this solution, right? So we can figure out what that original concentration was based on the milliliters and the number of moles. So we'll just go back to this equation again. Molarity equals moles over liters. We've got 0.00204 moles divided by, and you got to change that to liters, so 0.02, and then 3 zeros after it. Gotta watch our sig figs here. What? My computer, or my calculator's running out of batteries. So I'm ending up with a concentration here of 0.102 to the correct number of sig figs, I think. Okay, and that's, again, that's pretty close to what we were shooting for, because we were trying to make a 0.1 molar solution, right? But now we know exactly what it is. Okay, and then I'm guessing the last question is, oh, hey, we did it again. And this time we get a value of 0.100 molar HCl. So then once we average those two trials, then we would end up with 0.101 molar for the standardized HCl solution. Okay? So after having run through that pre-lab, I'm thinking that you guys will probably have a pretty good idea of how to design your procedure. And so it actually even gives you a little bit of a blurb after pre-lab problem number 9. It says, dilute the stock HCl and NaOH solutions to obtain solutions that are approximately 0.1 and 0.15, respectively, for the HCl and NaOH. Then standardize them. Write a procedure for carrying out these standardizations. Oh, well, even says here include 2 trials for each standardization, so they're not leaving that up to you. I will say what that means tomorrow is you're going to have to move fairly quickly because you got to do 4 titrations, basically. Okay? Yeah, we'll see if we get there. If we don't, I think that the Tums and Rolaids will go a little bit faster, but we'll just see how far we get tomorrow. Okay? It says also prepare a data sheet for the NaOH standardization, so it would be good to have an idea of how you're going to collect your data, and it tells you what things to put in that data table. All right? So if you would like to, you could actually write your procedure directly on the lab to give you a place for it. And then once you know that it's good, you can transfer it into your lab notebook. Or if you like to live dangerously, just put it on in there, right? And then hopefully it gets approved by me. All right, that's it. We'll see you guys in class tomorrow.